Hello and welcome to Earth Uncovered, a space where wonder feels at home and science takes a slower breath. Whether you're preparing to rest or simply letting your thoughts drift before sleep, I'm grateful you've joined. Tonight, we'll trace a question, not one that comes with tidy solutions or sharp edges, but one that encourages us to see the ground beneath us in a new way. What if Earth was designed? Now, I don't mean designed like something chosen from a catalog or pieced together like a do-it-yourself kit. Though imagining tiny cosmic blueprints is entertaining, that's not the point. I'm talking about something broader. What if Earth wasn't only the outcome of chance and blind forces, but instead shaped with intention, with order, through some kind of guiding process? How you picture that is open, maybe as an intelligent creator, perhaps a vast simulation, or even a natural algorithm beyond our comprehension. The focus here isn't on debate, but on gentle exploration. No raised voices, just quiet curiosity. And we're not in a hurry to decide. That's not the rhythm we keep here. Instead, we'll wander slowly across the ideas landscape, noticing both the hidden details and the wide patterns. And perhaps by simply asking the question, new perspectives will unfold, ways of seeing the world that may matter as much as any answer. To begin, let's start close to home, not with heavy theories or grand philosophies, but with the simple act of noticing daily life. Imagine your morning. You wake to sunlight spilling softly through the window. The air is cool but comfortable. You breathe in oxygen that your body seems perfectly matched to use. You feel thirsty, and water, clear, essential, without real flavor, is there, waiting for you. Step outside and you'll find plants, animals, the sky above, the steady pull of gravity, the right balance of temperature. Everything seems to align almost too perfectly, creating not just the possibility of life, but a comfort within it. We hardly notice. Most of the time, we take it for granted. Yet beneath that everyday ease lies something worth pausing over. Could it all be coincidence? Or is it arranged, like puzzle pieces falling into place a little too neatly? Science, of course, has offered thorough explanations. We know much about the early solar system, planetary formation, chemical evolution. We've gathered immense amounts of data, built simulations, and traced timelines across billions of years. It's a sturdy framework. And yet, even inside that framework, there are moments that feel strangely convenient. Think of it, Earth circles a remarkably stable star. It does so within a region scientists call the habitable zone, where liquid water can exist, vital for the kind of life we know. But that's only the beginning. Earth's tilt creates seasons. Its rotation keeps temperatures steady, preventing extremes. The moon's size not only drives tides, but also stabilizes that very tilt. A magnetic field shields the planet from dangerous solar radiation. The atmosphere holds just the right mixture of gases. Land and ocean are balanced in a way that supports life. And the list doesn't stop there. Each factor could have been drastically different. And if it were, life as we know it may never have arisen. Some point to the anthropic principle, the notion that the universe appears suited to life simply because we're here to notice it. If it weren't, we wouldn't exist to ask. It's a clean answer, yes, but it doesn't quiet the wondering. Is it really enough to shrug and say, well, it worked out because we're here? Or is there something deeper we're brushing past? None of this proves design. That's crucial to remember. Patterns aren't proof of purpose. But patterns can invite us to wonder whether purpose exists, or at least whether the question deserves space. So let's move forward not as defenders or doubters, but as explorers. Together, we'll walk through the hints and coincidences, the physics and philosophy, the numbers and the metaphors. And we'll move through this gently, without needing to land on a final conclusion. because whether Earth was intentionally shaped or not, it often behaves in ways that feel as though it was. That isn't a claim, but rather an observation, an invitation to ask, what would be different if Earth truly was designed? And what, perhaps, would remain the same? To explore that, we'll need to look both wide and deep. Of course, we'll talk about planetary physics, biology, and chemistry, but we'll also step into the realms of perception and story, and why human beings are so often drawn to the idea of a world created with intention. Part of that comes from religion, certainly, but not all of it. The longing to look up at the sky and feel that it carries meaning is older than any text, older than any temple. It may be something woven into us. Take symmetry, for example. We're naturally drawn to it. In faces, flowers, seashells, galaxies. When symmetry appears, our brains light up. It feels right. That instinct isn't proof of anything, but it offers a starting point. Why would a universe built on randomness keep producing patterns of order? And why does our sense of beauty so often align with what turns out to be efficient, functional, and mathematically elegant? This is where the conversation deepens. Even if you begin with a purely scientific perspective, you find yourself surrounded by questions that echo philosophy. The deeper we study biology, for instance, the more we see how finely tuned its systems are. Proteins fold with remarkable precision. DNA encodes vast amounts of information. Cells exchange signals with astonishing efficiency. None of it is flawless. Evolution leaves quirks and leftovers, but it works, and it works with a sophistication that can look a great deal like design. Now, design is a tricky word. It tends to summon images of a conscious being drafting blueprints or adjusting molecules. But it doesn't have to mean that. It might simply mean pattern, structure, direction, not chaos, but order with purpose behind it. Even if we don't know the source of that direction, the idea of Earth as designed doesn't require a single designer. It could mean something more abstract, a universe guided by deep logic that happens to generate life-supporting outcomes. Or perhaps it could mean something else entirely. There's also the possibility that Earth wasn't crafted from nothing, but rather chosen. Out of countless potential worlds, this one happened to support life, and here we are. But that immediately raises another question. How many possible Earths exist? Are we simply the lucky one in a trillion? Or is the universe filled with other worlds like this, each with its own version of balance and beauty? We don't know yet, but as we study exoplanets, and we've found thousands, we're starting to glimpse just how rare or common Earth-like conditions might be. So far, nothing is quite the same. Some planets are too hot, too cold, too massive, too small, or drenched in radiation. Some lack atmospheres, while others are smothered in gas. Some orbit stars that flare violently. The more we search, the clearer it becomes. Earth is unusual. Not impossible, not alone, but certainly not typical. And yet, what does typical even mean in a universe this vast? Perhaps the rarity of Earth's conditions is exactly what we'd expect if chance rules the cosmos. Or perhaps it hints at something deeper. Either way, the question keeps pulling us forward. Another layer worth considering is time. Not just space or location in the galaxy, but timing itself. Life didn't only require the right ingredients. It required the right sequence. A stable planet, yes, but also billions of years of relatively calm cosmic weather.
No overwhelming asteroid streaks, no constant solar storms.
A moon to steady the axis. Tectonic activity to recycle carbon. An atmosphere that shifted over eons in precisely the ways life needed. The timing had to align. Not impossible, but another piece of the growing puzzle. Different people interpret this in different ways. Some see divine intention, others see luck, and some believe it was inevitable, given enough time and space. The idea that Earth might have been intentionally arranged, whether directly or through some deeper framework of natural laws, remains fascinating. Not because it can be proven, but because it resonates so strongly with our lived experience. We are beings who design, who plan ahead, who imagine outcomes before they unfold. So when we encounter a world that feels carefully balanced, it's only natural to wonder if some kind of intention was involved. Still, caution is necessary. Patterns can emerge out of randomness. Our perception can mislead us. Just because something feels designed doesn't mean it truly is. And just because an event is unlikely doesn't automatically mean it was planned. Yet, the reverse also holds. Just because science can describe how something occurred doesn't mean we fully understand why it did, or whether a deeper structure lies beneath it. So the question we're exploring isn't about dismissing science or proving belief. It's about creating a space where both perspectives can ask the same question from different angles. What if Earth was designed? What would that change? What would remain the same? And what might that mean for how we live, how we view one another, and how we move forward? As we continue, we'll begin examining specific features of Earth that often fuel this conversation. The planet's orbital sweet spot, the uncanny role of the moon, the balanced composition of the atmosphere, the remarkable details of DNA, and the many systems that had to align for intelligent life to emerge. Each of these opens not only scientific questions, but deeper reflections about what we expect reality itself to be. Because when we ask whether Earth was designed, we're not only questioning planets and physics, we're touching something more profound. Beneath the science and speculation, it becomes personal. It's about how we interpret our place in the cosmos. Do we see life as a fortunate accident, or as something intentional? Do we see the world as a chain of coincidences, or as part of a greater order meant to be as it is? That's why this question carries a different weight compared to other scientific topics. If you ask how volcanoes erupt or why seasons shift, the answers are fascinating but not deeply emotional. This one is. But when you ask whether Earth might have been intentionally created, you are stepping into a conversation far older than telescopes or textbooks. It's a question humans have pondered since the very first time they gazed at the night sky, wondering what it all means. This is a question that echoes through philosophy, religion, and mythology. Stories of the Earth being shaped by hands, spirits, or voices that spoke the world into existence. While the details of these stories often conflict, they share a common thread. They reflect a fundamental human instinct, the desire to connect what exists with meaning, to turn observable facts into purpose. That instinct is not something to dismiss lightly. It's tempting to think of science and meaning as separate. One tells us how, the other tells us why. But the line between them is not always so clear. Consider something as basic as carbon. Life on Earth is built around this one element. Carbon forms the backbone of DNA, proteins, and all the complex chemistry that powers cells. It is astonishingly versatile. It bonds easily, forms long chains, creates stable molecules capable of carrying information and building structure. Without carbon, life as we know it could not exist. And when you look at how stars create elements, you see that carbon itself arises under an extremely narrow set of conditions. If the physics of nuclear fusion were even slightly different, a touch stronger or weaker, the universe might be full of hydrogen and helium, but no carbon. No carbon, no life, no us. Observing these coincidences prompts reflection, not because it proves anything, but because it highlights how specific conditions must be. And as we learn more about the laws of physics, it becomes clear that many values, mass, charge, gravity, the strength of forces, need to lie within very precise ranges for complex matter to exist at all. Not just life, but stars, planets, chemistry itself. This is sometimes called fine-tuning, and it leads to a quietly persistent question behind much of modern science. Why these numbers? Why this version of reality? One way to think about it is the multiverse. The possibility that countless universes exist, each with its own physical constants, and we just happen to inhabit the one where everything aligns perfectly. That perspective makes sense. Yet, we have no direct evidence for other universes, not yet. And even if we did find them, it wouldn't explain why our universe exists as it does. It would simply shift the question back one step. Another possibility is that these values aren't chosen at all. Perhaps they're embedded in some deeper structure we have yet to uncover. Either way, it's a mystery. Either way, we're confronted with a reality where conditions had to fall within certain ranges, and they do. This leads naturally to an even deeper question. Not just why Earth is the way it is, but why anything exists at all. Why are there physical laws? Why is there a universe with structure, patterns, and matter? Why is there something instead of nothing? No telescope or laboratory can answer this. And yet, it's a question we keep returning to. It's important to remember that science doesn't require purpose to function. You can study gravity without asking who created it. You can decode DNA without wondering who wrote it. But science also doesn't forbid these questions. It simply doesn't depend on them. For some, this creates a middle ground, a space to explore the universe through evidence while still entertaining the possibility that more is happening than we can measure. This is where the concept of design enters the conversation, not as a replacement for science, but as a lens, a perspective. It doesn't suggest we stop asking questions when we notice fine-tuning. It invites us to notice the fine-tuning itself, and perhaps, just perhaps, it hints at something deeper. Of course, opinions differ on what that deeper might be. Some envision a conscious designer, a god, an architect, a being with intention. Others see a form of inherent intelligence in the universe. Not a person, but a process that naturally moves toward order, complexity, and beauty. Others argue design is purely a human projection, a pattern we impose because we are wired to detect structure and stories. Across all these views, the central question remains the same. The interpretations vary. Even so, the question endures, quietly frames everything we do. Every scientific discovery, every satellite image, every equation or theory exists against the backdrop of this remarkable fact. We are here, observing. The world is not only there, it is intelligible. We can measure it, model it, predict it. Our brains, which evolved from simple nervous systems designed to find food and avoid danger, now model galaxies, build computers, and ask whether the universe has a purpose. Why should a species on a small rock in a remote galaxy corner be capable of grasping the rules of space and time? It doesn't prove anything, but it is striking. It raises the possibility that our understanding itself may be part of a larger pattern, that the universe may be structured in a way that invites comprehension. Not a claim, just a thought. Ultimately, these questions aren't threatening. They don't undermine science. If anything, they highlight how science can guide us to the very edge of mystery and encourage us to keep exploring beyond it. You don't need to have an answer for every question to make it meaningful. Sometimes, simply holding the question in your mind is enough. And this one, the idea that perhaps the world was built, arranged, or shaped in some deliberate way, is among the oldest questions humanity has asked. Yet it's also remarkably modern because today we have tools to peer more closely than ever before, to examine the fundamental building blocks of matter, the forces that govern nature, and the intricate dynamics of life. As we do, the question deepens, not because explanations run out, but because the explanations themselves are so intricate, precise, and finely balanced that they make you pause. They prompt reflection. Is this all just what happened to work? Or was it meant to happen this way? We can't answer fully, not yet, and perhaps never. But we can keep asking. We can trace the structures, the patterns, the logic, not to prove anything, but to understand, and perhaps along the way move a little closer to what lies at the core. When we turn our focus to Earth itself, not just its cosmic position, but its surface, its systems, the materials beneath our feet, we begin to see certain patterns. Some are geological, some chemical, some mathematical, and some structural. The closer we look, the more those patterns seem almost purposeful. It starts with the fundamentals. Take the planet's crust, for example. It's divided into plates that float atop a hotter, softer mantle layer, shifting slowly over time. This movement creates mountains, earthquakes, volcanoes, and even oceans. Without plate tectonics, the Earth's surface might have remained flat and static. Erosion would flatten it. Nutrients wouldn't cycle. Life, as we know it, might never have thrived. Plate movement also regulates carbon. Volcanoes release CO2, while weathering of mountains pulls CO2 back down. This balance affects climate, which in turn shapes the biosphere. Science has mapped this process in great detail. Yet, when seen from a wider perspective, it's hard not to marvel at the countless ways such a system could have failed. The planet didn't just need a solid crust. It needed one that cracked, floated, and moved. If the crust had been too thick, or the mantle too rigid, the tectonic plates wouldn't shift. Conversely, if the Earth had been too active, its surface might constantly renew itself, leaving no time for life to stabilize. Somehow, Earth landed in a balanced middle ground, neither too calm nor too chaotic. The more we examine how things are arranged, the more this idea of equilibrium appears. Take soil, for instance. It's a mixture of minerals, organic matter, water, and air, but the proportions must be precise. Too sandy, and water drains too quickly. Too clay-heavy, and roots struggle to breathe. The most fertile soils, the ones that sustain forests, crops, and diverse ecosystems, strike a delicate balance. This balance varies across regions, yet always stays within a narrow band of properties. Plants evolve to match the soil, or perhaps the soil adapts to the plants. This theme of coevolution recurs constantly. Not just plants and soil, but insects and flowers, fungi and trees, bacteria and animals. Systems that don't just function individually, but in harmony. Sometimes the fit is so precise it feels more like assembly than adaptation. Consider a simple seed. It carries all it needs: instructions, energy, and structure. It waits in the soil, responding to moisture, temperature, and light. When conditions align, it springs to life. Roots dig downward, stems reach upward. Biologically, we can describe this process, but the timing, sensitivity, and precision are remarkable. Even the shape of seeds, the ways they travel, stick, sink, or float, seem optimized, not perfectly, but very effectively. It's tempting to credit natural selection alone. Traits that succeed persist. Traits that fail fade. Yet selection works with what exists. It doesn't start from scratch. The starting materials matter. Look at life's building blocks. Carbon, nitrogen, oxygen, hydrogen. They're not only common but incredibly versatile. They bond easily, store energy efficiently, and form molecules capable of looping, twisting, and replicating. Chemistry follows rules, and in our universe, those rules seem to favor complexity. Complexity isn't guaranteed, but once it emerges, it has room to expand. And Earth, for reasons not entirely understood, seems to give it a head start. Take water. Not rare, not exotic, but it has remarkable properties. It expands when frozen, allowing ice to float and life to survive under frozen lakes. It has high specific heat, stabilizing temperatures. It dissolves more substances than almost any other liquid, making it ideal for chemical reactions. All these properties stem from the angle between two hydrogen atoms and one oxygen atom. Change that angle slightly and water behaves completely differently, and so does everything that relies on it. Then there's the concept of fractals, patterns that repeat across scales. Rivers, mountains, coastlines, tree branches, blood vessels. These patterns aren't just aesthetically pleasing. They're efficient, transporting resources across space with minimal material. Trees use fractal branching to move nutrients. Lungs use the same principle for air. These patterns follow consistent mathematical rules. Some call it convergence. Others suspect something more deliberate. Fibonacci sequences offer another example. Spirals and shells, pine cones, sunflowers, galaxies. Not universal but frequent, especially in growth processes. They optimize packing and expansion. Mathematics appears repeatedly in biology, raising intriguing questions. Does the universe follow math because it must? Or does math describe it so precisely because both arise from the same underlying principle? This is where the idea of blueprints enters. Not a literal blueprint, but a pattern of consistent systems producing reliable outcomes. Earth is neither random nor purely chaotic. Order exists here, layered functionality, from soil chemistry to planetary motion. Science depends on it. Yet, it also sparks wonder. Might this regularity hint at something beyond? Patterns can emerge from chaos, yes, but often under very specific initial conditions. Change them slightly, and the outcome shifts entirely. It makes you wonder, what were the starting conditions here? Why do these particular laws exist? Why a world where minerals naturally form crystals, plants instinctively respond to light, and animals evolve eyes? This isn't suggesting anything supernatural, but the more we examine Earth's structure, the blueprints in its soil, the cycles of its systems, the more the question arises. Could this have been arranged? Not through magic or miracles, but through a process we don't yet fully understand. One where design exists not as a deliberate choice, but as a principle, a natural inclination towards systems that support life. We don't need to answer this now. We're here to observe, not conclude. And what becomes clear is that Earth is not just a random mix of materials. It's an intricately connected system, full of rules, balances, and alignments that consistently lean toward stability, growth, and resilience. That doesn't mean it's perfect, far from it, but it works, and it works in ways that feel finely tuned. When people ask why life thrives on Earth and not Mars or Venus, they often mention the so-called Goldilocks zone. This refers to the region around a star where temperatures are just right, not too hot, not too cold, for liquid water to exist. Since water appears essential for life as we know it, any planet comfortably within this zone is at least a contender. Earth sits near the middle of that range, close enough to the sun to avoid freezing, far enough to avoid boiling. Its star is stable and long-lived, allowing billions of years for complex ecosystems to develop. It's tempting to think the universe simply hit the bullseye, but the more you examine it, the more intricate the picture becomes. The habitable zone isn't fixed. It depends on the star's size and brightness. Smaller, dimmer stars have tighter, closer zones but flare more, bombarding planets with radiation. Larger, hotter stars burn fuel faster, giving less time for life to evolve. Earth's sun is roughly average. Stable, bright, and long-lived. Not the only kind that can host life, but certainly one of the better ones. Then there's Earth's orbit. The planet doesn't just sit at the right distance, it maintains that position. Its path around the sun is nearly circular, keeping solar energy fairly constant throughout the year. Some variation gives us seasons, but too much would create extreme climate swings. A slightly more elliptical orbit could have rendered vast regions uninhabitable. Yet Earth wobbles just enough and tilts just enough to stir life into motion without destabilizing it. Distance and orbit are just the beginning. A planet in the habitable zone can still be lifeless. Mars, for example, is at the outer edge of this range. Ice exists, but the atmosphere is gone. Temperatures are cold, and radiation exposure is high. Life's ingredients were there, but the kitchen failed. Venus, on the inner edge, is similar in size and composition to Earth, but its dense carbon dioxide atmosphere creates a runaway greenhouse effect. Surface temperatures can melt lead, and clouds of sulfuric acid envelop it. If Earth is a warm cup of tea, Venus is a boiling kettle screaming endlessly. This illustrates how narrow Earth's window truly is, not just in distance, but in how its systems interconnect. The atmosphere traps heat, but not excessively. Oxygen, nitrogen, and carbon dioxide exist in just the right ratios. Oceans regulate climate, weather systems distribute heat, and the greenhouse effect operates without running out of control. This is not a fragile equilibrium, but a dynamic one. Systems shift, adjust, and compensate. Flexibility is part of Earth's resilience. But again, things didn't have to fall into place this way. Small variations in early conditions could have created a planet that looked entirely different. If we rewind far enough, we reach the birth of the solar system itself, the swirling cloud of gas and dust that eventually formed the sun and its planets. Within that cloud, Earth's final position was shaped by a complex mix of gravitational pulls, collisions, and residual material. It could have emerged farther out, becoming a frozen rock, or closer in, resembling Mercury. But instead, it formed in a zone where water could remain liquid and where conditions allowed life to begin and persist. Some see this as pure chance, countless rolls of cosmic dice, and that is a valid perspective. Yet others observe the outcome. A planet with temperatures, chemistry, and history seemingly just right, and wonder whether the cosmic dice might have been subtly weighted, not through unfair manipulation, but in a manner that suggests underlying direction. Perhaps not deliberate, but not indifferent either. This perspective opens new questions. Is the Goldilocks zone a rare occurrence, or common across the cosmos? Do other stars host planets in the same favorable range? So far, thousands of exoplanets have been discovered, and some appear to sit within their stars' habitable zones. But beyond that, we know very little. Their atmospheres, water content, magnetic fields, climate stability, and surface conditions remain mostly unknown. Even if all the right ingredients exist, we cannot tell whether life emerged or even had the chance to emerge. Thus, Earth remains our primary example, and the closer we examine it, the more finely tuned it appears. Not perfect, climate shifts, natural disasters, and ecosystem collapses still happen, but on the whole, balance prevails. Life continues, not only simple organisms, but complex, conscious beings that ponder their own existence. Just right sounds deceptively simple, but it encompasses hundreds of interacting systems: geology, weather, magnetism, chemistry, and biology, all aligned to support life. It's not just a matter of location, but everything that the location allows. Even so, this doesn't necessarily prove design. Perhaps it's merely chance, and life is rare but not impossible. Earth could simply be a fortunate alignment. That is the standard scientific viewpoint. Yet, there is also a quiet intuition, not a conclusion but a persistent sense, that this alignment hints at something deeper, perhaps reflecting the way the universe inherently operates or tends to operate. If we entertain the idea of design, what might it aim for? Life? Complexity? Balance? a system capable of maintaining itself long enough to become intricate and meaningful. This doesn't imply perfection or ease. Earth is not a utopia, but it is exceptionally positioned for something rare, intricate, and remarkable to unfold. Once you shift focus from Earth's position in space to the nature of Earth itself, the planet's internal structure becomes central to the story. Not just the landscapes we traverse, but the full anatomy, from the iron core to the contours of its orbit. If Earth was intended to nurture life, it's reasonable to think that this structure plays a critical role. Even if no conscious design was involved, the arrangement of its components raises fascinating questions. Much of this begins at the center. The Earth's core is primarily iron and nickel, split into a solid inner core and a liquid outer core. The motion of the outer core generates Earth's magnetic field, which protects the surface from solar and cosmic radiation. Without this shield, charged particles would constantly bombard the planet, stripping away the atmosphere, damaging DNA, and making life extremely difficult, if not impossible. The magnetic field doesn't appear by chance. It's produced by the geodynamo. Earth's rotation sets the molten metal in motion, generating electric currents, which in turn create the magnetic field. For this system to function, several conditions must align. The right materials are necessary. A certain amount of internal heat is required, sourced from radioactive decay and residual energy from the planet's formation. The planet's size must be just right. Smaller worlds cool too fast. And rotation must exist, but not excessively. Earth completes a rotation every 24 hours, sufficient to keep the core active and maintain surface stability. Any deviation could have catastrophic consequences. A slightly smaller, slower, or less metallic planet might lose its magnetic protection entirely, as happened with Mars. Mars likely had a magnetic field early in its history, but it cooled too rapidly. Its core stopped churning, the shield vanished, and over time, the atmosphere and surface water dissipated. Above the core lies the mantle, slowly flowing and driving tectonic plate motion. These plates, as previously discussed, are vital for recycling minerals, shaping continents, forming mountains, and regulating the carbon cycle. They also require a precise balance of heat and rigidity. Too soft, and the crust would fracture uncontrollably. Too rigid, and nothing would move. Earth's mantle seems tuned perfectly, dynamic yet stable. Continental drift, collisions, and reformation create diverse climates, isolate ecosystems, and fuel biodiversity. Without these movements, Earth's surface might be monotonous and lifeless. Even the crust plays a pivotal role. Relatively thin, only a few kilometers under oceans, slightly thicker under continents, it hosts all surface life. Its composition contains essential elements: carbon, phosphorus, sulfur, calcium, potassium. Many of these didn't originate from Earth's initial formation. They arrived later during the late heavy bombardment, when asteroids and comets delivered water, organic molecules, and other foundational ingredients. Had that event unfolded differently, life as we know it might never have begun. Too many collisions early on, and Earth's surface might never have cooled enough to allow stable conditions. Too few, and the planet might have lacked the raw materials necessary for life. Somehow, Earth received just the right mix, a combination of rocky and icy bodies that enriched what was already present. Another moment where the alignment wasn't guaranteed, yet it occurred. Surrounding all this is the atmosphere, serving both as a shield and a life support system. It traps heat to keep the planet temperate, protects against smaller space debris, and holds the gases needed for respiration and photosynthesis. But it didn't begin this way. Early on, the atmosphere was likely dominated by carbon dioxide, methane, and ammonia, hostile to modern life, yet suitable for primordial microbes. Over time, photosynthetic organisms began producing oxygen, gradually transforming the atmosphere into what we know today. This transition, known as the Great Oxidation Event, could have gone differently. Oxygen is reactive. Too much can be harmful, yet in balanced quantities, it enables complex metabolism, paving the way for multicellular life. The resilience of Earth systems during that transformation demonstrates the power of feedback loops. Both positive and negative feedback maintained conditions within a functional range. Even now, the balance of carbon dioxide and oxygen is managed dynamically. Forests, oceans, and soils act as carbon sinks, while respiration and volcanic activity return gases to the mix. The result isn't perfect equilibrium, but a self-regulating system over long timescales. In this sense, Earth's surface behaves less like a machine and more like a living, responsive organism. Water, too, follows this principle. Its distribution across the planet is uneven but effective. Oceans cover roughly 70% of the surface, moderating temperature and cycling nutrients. Freshwater exists in rivers, lakes, ice caps, and aquifers, sustaining both marine and terrestrial ecosystems. This cycle relies on planetary mechanisms of precipitation, evaporation, and flow, governed by geography and solar energy. Even the planet's axial tilt of approximately 23.5 degrees dictates how sunlight reaches different regions, creating seasons. The moon stabilizes this tilt. Without it, the angle might wobble chaotically, triggering extreme climate swings. Instead, life experiences a reliable rhythm. Migration, hibernation, flowering, all synchronized to sunlight and the year cycle. When all these elements are considered together, Earth is not merely a planet in space, but a sophisticated, multi-layered system. Earth is not just a passive rock floating in space. It generates its own magnetic field, maintains its own temperature, cycles essential resources, and sustains life. In essence, it constructs the conditions necessary for its own habitability and preserves them through feedback loops and dynamic flows. None of this proves anything beyond observation, yet it invites a fresh perspective. Rather than seeing Earth as merely a fortunate combination of traits, one might perceive an underlying internal logic, an arrangement that naturally leads to life-supporting outcomes. Whether this logic was inherent, evolved over time, or is part of a broader framework remains an open question. Tides are more than simple ocean motions. They distribute nutrients throughout coastal ecosystems, help regulate shallow water temperatures, and may have even contributed to life's origins by creating wet-dry cycles that encouraged chemical reactions. The ebb and flow of the oceans shapes coastlines, influences weather patterns, and affects the behavior of countless species. There's also a subtle timing effect. The moon's gravitational pull gradually slows Earth's rotation. Billions of years ago, a day on Earth lasted only about 6 hours. Over time, tidal friction stretched that day to the 24 hours we know now. This process continues today, albeit at a rate too slow to notice within a human lifetime, but over long periods, it has likely contributed to climate stability. Light, too, plays a biological role. Many organisms use the lunar cycle as a clock, coordinating migration, reproduction, feeding, or sleep. Coral reefs spawn according to moonlight. Insects navigate by it. Predators and prey alike adjust their activity based on nighttime brightness. The moon imposes a rhythm woven into the biology of countless species. And all of this comes from a satellite that, statistically speaking, might not even exist. Large moons like Earth's are rare among rocky planets. Mars has 2 small, irregular moons, likely captured asteroids. Mercury and Venus have none. Within our current understanding of planet formation, large moons are an unusual outcome. Yet Earth has one, and not just any moon, but one remarkably suited to its purpose. This brings us back to the question of Earth specificity. No one suggests the moon was placed with tools or blueprints, but the fact that a life-supporting planet coincides with a stabilizing satellite is striking. Its formation, orbit, and effects all add a layer of complexity to why Earth has such precise characteristics. Some argue that life might still have arisen without the moon, but complex multicellular life could have faced greater difficulties surviving chaotic climates, and the long-term evolution of intelligent species would have been less likely without stability. Adapting to seasons is one challenge. Adapting to a tilt swinging wildly over tens of thousands of years is another. Some even speculate the moon helped protect Earth from asteroid impacts or influenced heat distribution in the core, affecting the geodynamo that drives the magnetic field. These ideas are harder to prove, but they reinforce that the moon is more than a passive companion. It's an active part of Earth's history. Even now, it drifts away at about 4 centimeters per year. That change is tiny in a human lifetime, but over geological time, it matters. In a few billion years, total solar eclipses, where the moon perfectly covers the sun, will no longer occur. Like many features of Earth, this alignment exists within a narrow window, significant but temporary. Meanwhile, gravity quietly persists. It's always present, always effective, but usually unnoticed. You feel it when something falls, when you step on a scale, or when your coffee tips over, a constant reminder that invisible forces shape our world every moment. When it comes to constructing a planet and keeping everything on it in balance, gravity is far more than just background. It's the hidden scaffolding beneath the visible structure. By the standards of physics, gravity isn't strong. Compared to electromagnetism or nuclear forces, it's weak. A tiny magnet can lift a paperclip against the full gravitational pull of Earth. But what gravity lacks in raw strength, it compensates for with reach. It never switches off, never gets blocked, and acts on all objects with mass. This steady persistence is what makes it a master organizer. Without gravity, Earth wouldn't be spherical. It might not even qualify as a planet. The matter that would become Earth would linger as a diffuse cloud, never condensing into a solid body. Planets form because gravity gradually pulls together dust and gas, compressing it until pressure and heat transform it into a dense sphere. That same force drew in the core, mantle, and crust, not as random layers, but in an arrangement reflecting their densities. Heavier elements like iron and nickel sank toward the center, while lighter materials floated outward. Gravity sorted Earth by weight, and that sorting continues to govern its behavior today. Gravity's role extends beyond shaping Earth itself. It keeps the moon in orbit, pulls on oceans to create tides, and locks Earth into a stable path around the sun. Without it, the planet wouldn't just lose shape, it would lose everything holding it together. No orbit, no seasons, no shielding from the vacuum of space. The orbit deserves special attention. Earth's path around the sun isn't arbitrary. It's a stable, nearly circular trajectory. Such an orbit arises from balanced forces, the planet's forward motion and the sun's inward gravitational pull. Too fast, and Earth would escape into space. Too slow, and it would spiral inward. But its speed and position align perfectly, creating a continuous fall that never ends. This stability allows long-term climate patterns to exist and provides a reliable framework for seasons, day length, and solar energy. Life evolves around these cycles, and those cycles depend entirely on gravity doing its job. The moon's pull generates ocean bulges, producing tides, while even the solid Earth shifts slightly in response, a phenomenon called Earth tides. These minute motions create stresses in the crust that, over millennia, influence tectonic activity. In essence, Gravity not only holds everything together but also guides motion and evolution. Even Earth's axial tilt, the angle behind our seasons, is stabilized by gravitational interactions. Without this, the planet might gradually tip or spin erratically. The combined pull of the sun and moon keeps the tilt within a narrow range, offering a predictable environment, not rigid, but bounded, allowing controlled variation. On smaller scales, gravity shapes mountains, rivers, glaciers, and rainfall, sculpting landscapes over eons. Valleys, cliffs, plains, all of it reflects matter slowly responding to the pull of gravity. Even the way trees develop is guided by gravity. Roots extend downward, while stems push skyward, all orchestrated by tiny cellular sensors that detect gravitational pull. These effects are easy to miss because they unfold slowly. Gravity doesn't make noise, it doesn't flicker or shine, yet its influence is constant, linking every aspect of Earth's systems, from the rotation of the core to the positioning of clouds in the sky. Then there's the human aspect. Our own bodies are finely tuned to Earth's gravity. The density of our bones, the circulation of blood, even the way we maintain balance while standing, all of it relies on a specific gravitational force. In low gravity, muscles atrophy, fluids shift, vision can alter. That's why astronauts experience a range of physiological changes in space. Their bodies are adapted to the 9.8 meters per square second pull on Earth. Remove it and everything must recalibrate. If Earth were slightly more massive, gravity would intensify. Life might need shorter, sturdier bodies. If gravity were weaker, the atmosphere could thin or even drift away over time. Planetary size and mass are not abstract. They form the framework that makes surface life viable. The atmosphere remains stable, water flows as it does, humans and animals grow to specific sizes. Even birds and insects fly with wings evolved under these precise conditions. Beyond our planet, gravity continues to play the role of master architect. It holds galaxies together, governs stellar motions, and bends light from distant sources. Gravitational lensing, a bending of light caused by massive objects, is one of the key ways we infer the presence of dark matter. We don't see it directly, but we detect its effects. Similarly, while gravity itself is invisible, its presence is felt everywhere that matter rests or moves. In a universe that often appears chaotic or random, gravity provides a subtle order. Not perfectly mechanical, but steady and persistent. It doesn't explain everything, yet it establishes the conditions for almost everything else to exist. Without it, none of this could be. Consider water, seemingly simple, 2 hydrogen atoms and 1 oxygen. Yet its behavior is far from ordinary. On Earth, water is ubiquitous. It fills oceans, shapes weather, carves landscapes, and moves through every living cell. It is essential for life as we know it. But when we examine its properties and how rare they are, it becomes harder to view water as mere chance. One of its most striking features is its ability to exist in all 3 states, solid, liquid, and gas, under naturally occurring Earth temperatures. That's far from ordinary. Most substances prefer a single state or require extreme conditions to change, but water can freeze, melt, and evaporate within a narrow temperature range that fits neatly with Earth's climate. On its own, this might not seem extraordinary until you consider what these phase changes actually accomplish. When water evaporates, it absorbs heat, helping to cool surfaces. When it condenses into clouds, it releases that heat, warming the atmosphere. This dynamic plays a major role in distributing energy across the planet. It drives weather patterns, moderates temperature, and prevents the climate from swinging too far in any single direction. Another critical property is water's high specific heat. This allows it to store large amounts of energy before its temperature changes, turning oceans and lakes into thermal buffers. They absorb heat during summer and release it in winter, smoothing temperature extremes. Without this, day-to-night or summer-to-winter variations would be far harsher. Perhaps water's most famous quirk is that it expands as it freezes. Most materials become denser when they cool, but water begins to expand just before freezing, causing ice to float. This single characteristic has enormous consequences. Lakes and oceans freeze from the top down, forming an insulating layer that protects life beneath. Aquatic ecosystems survive the winter, and when the ice melts, it doesn't sink to disrupt everything below. Water's role as a solvent is another marvel. Known as the universal solvent, it dissolves more substances than any other liquid, transporting minerals, nutrients, and gases through soil, rivers, and living organisms. Inside bodies, water carries molecules in and out of cells, moves hormones, regulates temperature, and maintains structure. Its polarity, having slightly positive and negative ends, enables hydrogen bonding, which influences protein folding, DNA stability, and enzyme function. These properties are not accidental. They arise from the H2O molecule's geometry, electron distribution, and bond nature. Slight changes could make water far less flexible and less supportive of life. While hydrogen and oxygen are abundant in the universe, water in the vast, stable surface quantities found on Earth is rare. Oceans cover roughly 70% of the planet, and they have persisted for billions of years. No other solar system planet has a comparable amount. Mars has ice and may have had liquid water, but it no longer exists on the surface. Venus might once have had oceans, but its atmosphere transformed, boiling them away. Earth's water endured, staying within a narrow temperature window long enough to maintain oceans, weather, and a full hydrological cycle. Evaporation, condensation, precipitation, and runoff moving constantly between land, sky, and sea. This cycle sustains ecosystems, nourishes forests, fills rivers, shapes coastlines, and erodes mountains into soil. Nutrients are transported from place to place. Without this system, Earth would be barren, plants would die, and food chains would collapse. Water is not merely a life ingredient. It is the system life flows through. Water's interaction with light also matters. Transparent to visible light, it allows sunlight to penetrate oceans, fueling photosynthesis in aquatic plants. Were it opaque, underwater ecosystems would live in darkness, but water lets in just enough light while filtering harmful ultraviolet rays. Rain, snow, clouds, and fog, all components of water's perpetual movement, affect temperature, visibility, behavior, and mood. They influence migration, agriculture, and landscape evolution. Timing, how often it rains, how long snow lasts, when dry seasons begin, is linked to geography, winds, and planetary tilt. Earth's climate and water systems operate in a feedback loop, supporting a diverse array of life forms. Even in the deepest oceans, far from sunlight, life thrives. Hydrothermal vents release heat and minerals, sustaining unique ecosystems where bacteria convert chemical energy into food, feeding fish, crustaceans, and other extraordinary organisms. These environments remind us that life may not always require light, but it always requires water. Earth's most common liquid remains its most essential. It's remarkable that a substance so deceptively simple in structure turns out to be so intricate in function. The conditions required to keep it circulating, atmospheric pressure, surface temperature, planetary mass, are all intimately connected. This doesn't necessarily imply that water was purposefully designed to act this way. Perhaps life merely adapted to the properties water already possesses. Yet even that leaves an intriguing question open. Why does water behave this way at all? Why does a molecule made of just 3 atoms become the foundation for a vast, interconnected system of life in a universe with different physical rules? Water might not exist in another universe, or it might behave differently, or another medium might take its place. But here, under these conditions and on this planet, water fulfills its role nearly perfectly. It flows, transports, dissolves, freezes, and transforms, quietly orchestrating the background processes life relies on every moment. Looking closer at life itself, patterns begin to emerge in its forms. How trees branch, shells spiral, petals align, crystals grow. These aren't merely resemblances. They are repeated structures that appear across scales and environments. Some are symmetrical, some spiral, some adhere to ratios that can be expressed numerically. While physical processes explain these shapes, their consistency is striking. Symmetry is often the most obvious. Faces, bodies, leaves, insects, snowflakes. Symmetry appears everywhere. When one side mirrors another vertically, horizontally, or rotationally, we recognize it as symmetrical. This balance can have practical effects, like distributing weight evenly or facilitating movement. Symmetry also resonates with perception. Humans are wired to detect it rapidly, and symmetrical faces are generally perceived as more attractive. We apply symmetry in design, architecture, and symbols. It signals order, familiarity, and completeness. In nature, symmetry frequently serves a functional purpose. Butterfly wings match because they develop together. Starfish exhibit radial symmetry, aiding movement and environmental response. Leaves often grow in pairs to optimize light capture. Even many viruses employ symmetrical protein shells, not for aesthetics, but because symmetry is efficient. It allows repeated use of the same genetic instructions, a material shortcut. Create one unit, replicate it multiple times. Yet not all natural structures are mirrored. Some of the most fascinating forms follow a spiral pattern. Spirals appear in many places, from the whorls of a snail shell to the swirling arms of hurricanes and whirlpools, from the vast spirals of galaxies to the compact geometry of pine cones and sunflower heads. They show up in fingerprints, in the curves of animal horns, and almost anywhere growth or expansion is involved. Spirals provide a clever solution. They allow structures to grow outward while maintaining compactness. As an organism adds material, a new scale, petal, or layer, the spiral accommodates it seamlessly, without disturbing the overall structure. Many spirals follow a mathematical pattern known as the Fibonacci sequence, where each number is the sum of the 2 preceding ones. 0, 1, 1, 2, 3, 5, 8, 13, and so forth. This pattern appears in the arrangement of petals, the branching of trees, and the packing of seeds. Ratios of consecutive Fibonacci numbers approximate the golden ratio, a proportion that recurs frequently in both nature and human art. It isn't universal, but it is common enough to capture attention. These patterns require no conscious intelligence to emerge. They arise naturally from growth, competition, and efficiency. For instance, a plant growing new leaves may adopt a spiral configuration to minimize shade on lower leaves. This arrangement often aligns with the golden angle, distributing elements optimally. It wasn't designed for beauty, it simply works. Yet, the result is aesthetically pleasing, which leads some to refer to it as sacred geometry. Sacred geometry is a term used in different contexts, sometimes spiritual, sometimes symbolic, and sometimes poetic, to describe patterns that appear meaningful due to their form. Circles, triangles, spirals, and hexagons appear in religious art, ancient architecture, mandalas, and monuments. Yet the same shapes also exist in snowflakes, honeycombs, and coral reefs. The similarity between natural geometry and human creations may not be coincidental. We might replicate what we observe in nature, or perhaps our brains are simply tuned to recognize these forms as harmonious, complete, and pleasing, even if we don't consciously understand why. Hexagons illustrate this well. Bees construct hexagonal hives because the shape efficiently divides space into equal areas with minimal material, creating a strong and stable structure. Hexagons also emerge in basalt columns like the Giant's Causeway or in foam bubbles, all governed by physics without bees involved. Crystals behave similarly. Their atoms naturally organize into repeating patterns, forming cubes, prisms, or intricate branching forms. These shapes are dictated by internal molecular rules, guided by temperature, pressure, and chemical bonding. The result is a form that appears both random and deliberate. Fractals are everywhere, showing patterns that repeat across different scales. Tree branches split into smaller twigs, rivers branch into tributaries, lightning forks across the sky, veins spread through leaves and skin, and lungs divide into finer airways. Each layer mirrors the larger structure, creating a miniature version of the whole. Fractals are highly efficient for distributing energy or resources. They allow a system to reach countless points from a central origin. Often, these patterns emerge simply from repeating straightforward rules. What makes these structures so fascinating is that they require no elaborate design to exist. They arise naturally from feedback loops, physical constraints, and iterative processes. The behavior of materials under specific conditions produces them, yet they appear purposeful. They give rise to a kind of visual logic, a coherence that seems too consistent to be coincidental. There is also harmony in how these forms interlock. Branches fill space without colliding, spirals pack seeds perfectly, and snowflakes develop along symmetrical lines. These outcomes are not random, they are structured, and when such structure accumulates, it suggests that order itself is intrinsic to the natural world. Some scientists propose that shapes like spheres, spirals, or hexagons are preferred solutions in physical systems. Given time and freedom, matter tends toward these forms because they are stable or efficient. That explanation is helpful, but it also raises a bigger question. Why do these efficient solutions so often support life? Why are they present in both microscopic cells and massive celestial structures? There is no need to assume mysticism to notice the pattern, yet it is remarkable that the laws of the universe create outcomes that are simultaneously functional and aesthetically consistent. Shapes that optimize growth or energy also resonate with human perceptions of beauty. The most effective designs recur repeatedly, suggesting a natural framework or principle guiding possibility, probability, and sustainability. Whether derived from physics, mathematics, or some deeper principle, this framework is embedded in how matter organizes itself, contributing to the sense of interconnectedness in life. Looking at life's external forms, it's striking how cohesively everything fits together. Yet, delve inside a cell into its nucleus and molecules, and the sense of precision intensifies. Biological systems are layered, interlocking, and coordinated. They don't just work, they function in synchrony. At the center of it all is DNA, deoxyribonucleic acid, the molecule carrying genetic instructions. Every living organism uses DNA, or its close cousin RNA, to store and transmit information about building and maintaining life. DNA is more than a substance. It's a code. It consists of 4 nucleotides: adenine, thymine, cytosine, and guanine. Sequenced in specific orders, they dictate how proteins are produced, which in turn drives cellular machinery. DNA is often likened to a language, not merely because of its limited alphabet, but because of its structure, syntax, and meaning. Even small changes in DNA can alter protein shape and function, sometimes subtly, sometimes profoundly. The same gene can be reused across organisms with slight variations, performing similar tasks. The reading, copying, and interpreting of DNA is so orderly it feels more like a system or process than a chemical reaction. DNA is not merely storage, it is life in operation. It's all about regulation. Within the genome, there are sequences that serve as start and stop markers, indicating precisely when a gene should be active. Regulatory genes oversee other genes, turning them on or off as needed. Error-checking systems constantly monitor copying processes and repair mistakes. Remarkably, all of this activity takes place inside a structure just a few micrometers across, in every cell of every living organism. The sophistication of this organization draws attention not because it's mysterious, but because it is extraordinarily effective. The primary explanation remains evolution through natural selection. Small genetic variations arise, and those that enhance survival tend to persist and propagate. Over time, this process produces complexity. Evidence is abundant in fossils, laboratory experiments, and shared genetic material among related species. Yet, even within this framework, the cellular machinery itself is striking. Proteins fold into precise three-dimensional shapes dictated by amino acid interactions. This folding is essential. Misfolded proteins often fail to function. Within living cells, folding occurs automatically, guided by the amino acid sequence and assisted by chaperone molecules. There's no consciousness involved, yet the process operates with a remarkable elegance. It is not random trial and error, it is thousands of components synchronizing at the right time. Enzymes, for instance, accelerate chemical reactions. Without them, vital reactions would occur too slowly to sustain life. With enzymes, reactions happen millions of times faster. They are highly selective, fitting specific substrates like a key in a lock, and life relies on that selectivity to control timing and function. Molecular motors, tiny protein machines, move cargo, spin, pump, or operate gates inside cells. They convert chemical energy into motion, functioning much like mechanical devices on a macroscopic scale. These systems are not unique to complex organisms. Bacteria, plants, and all living things utilize variations of the same basic tools. While the components differ, the principles are consistent, supporting a shared origin and evolution. But questions remain. Where did the original instructions come from? The first sequences, proteins, and membranes, the origin of life from non-living matter, is an active area of research. Proposed models include formations on clay surfaces, deep-sea vents, or ice-covered lakes. Progress has been made, but no theory is universally accepted. Life requires more than molecules. It demands systems capable of copying, regulating, responding, and evolving. The transition from chemistry to biology remains one of science's most challenging frontiers. This gap between random molecules and functioning cells leads some to consider whether biology exhibits signs of engineering. Not in the human sense of machines, but in the sense that each piece is exceptionally well suited to its role. Genetic code is executable. It stores instructions, modifies itself, and adapts in real time. DNA packing is astonishingly efficient. If stretched, human DNA would be roughly 2 meters long, yet it fits into a microscopic nucleus, wrapped, looped, and organized for immediate access. That's not disorder, it's management. Beyond DNA, cells maintain multiple layers of feedback loops and signaling networks that control growth, division, repair, and death, maintaining balance in living organisms. Cells respond to damage, stress, nutrient shortage, and infection. They communicate with each other using chemical signals, adjusting their behavior depending on the circumstances. Mistakes do occur, but the system doesn't rely on perfection. It relies on resilience. Life isn't flawless. Mutations can cause illness, systems can fail, yet life persists. This persistence itself reflects a form of engineering. Adaptive rather than rigid, dynamic rather than static. This does not imply that cells were created by a conscious designer. It may simply be that the systems that survive are the ones that work, which is entirely plausible. Yet, when you observe the sheer degree of coordination, the analogy extends beyond a factory, a city, or a machine. It resembles a code base, a set of instructions that not only builds itself but also maintains and updates itself. Biology, like software, is layered. There's the raw code, the DNA sequence. There's the operating system, the cellular machinery interpreting that code. There are inputs and outputs, error correction, feedback loops, and networks of interactions among genes, proteins, cells, and organs producing behaviors, responses, and even thoughts. This reframes the question. Perhaps it's not whether biology was engineered, but whether engineering and biology can be understood in comparable terms. Is this comparison merely metaphorical? Or does the structure of life hint at a deeper connection between systems evolved naturally and those designed intentionally? The answer remains open. Yet, the deeper one examines life's code, the more structured it appears. Not random, not improvised, but layered, regulated, and intricately integrated. All of this operates less like a simple string of code and more like a full programming language, one that conveys instructions within context, supports layers, and enables conditional behaviors. In computers, code is compiled and executed. In cells, DNA is transcribed and translated. Both systems require machinery capable of interpreting a set of symbols. Both rely on precision, structure, and timing, and both can malfunction if rules aren't followed. Yet DNA isn't read all at once. Only a small portion is active at any moment. Different genes are expressed in various cell types, at distinct developmental stages, and in response to specific signals. The same DNA sequence can yield vastly different outcomes depending on its location in the body or the surrounding environment. This flexibility is essential for complex life and contributes to the sense that DNA is more than mere data. It behaves as a coordinated system. Remarkably, this system is nearly universal. All known life on Earth uses the same basic genetic code. The same 4 nucleotides, codon structure, and translation rules. A codon, a trio of bases, codes for one amino acid. There are 64 possible codons, but only 20 standard amino acids. This redundancy allows some codons to be synonyms while others act as signals. Start here, stop here. This entire framework is shared by bacteria, plants, animals, and all life forms, suggesting a common origin. At some ancient point, life settled on one code, and evolution carried it forward across every lineage. Yet a question arises: why this code, this structure? Scientists have investigated whether the genetic code is optimized, designed to minimize errors and maintain flexibility. Evidence suggests it is remarkably efficient, not perfect but highly robust against mutations and capable of supporting variation. In other words, life didn't just pick any code. It selected one that works extremely well. Whether this choice arose naturally or through constraints that favored certain arrangements is still debated. Either way, the code has functioned across all life forms for billions of years. There is also interpretation. Humans did not invent DNA, but we learned how to read it, translating chemical sequences into actionable information. That revealed astonishing properties. Not only complexity, but logic. Not just molecules, but instructions. This insight birthed fields such as genetics, molecular biology, and bioinformatics. Today, we manipulate DNA with tools like CRISPR, redesign genes with precision, synthesize sequences, and observe their function. In some ways, we are now writing in the language of life, but we did not invent the language itself. It existed long before us. This is where design enters discussions. Not because DNA appears manufactured like a chip, but because it operates with purpose. It handles information in ways reminiscent of software, logic circuits, or pre-planned instructions. It isn't random noise. It's structured, purposeful, and present in every living organism. Another layer to consider is meaning. In human languages, meaning arises from intention. Someone writes or speaks to convey a message. With DNA, there is no conscious intent. This meaning is functional. A sequence matters because it produces an effect. It builds a protein, triggers a chemical reaction, or allows a process to proceed. But does this functional meaning qualify as a language? Or is it simply a metaphor borrowed from human communication systems? This ambiguity is part of what makes the study of DNA so fascinating. DNA can be viewed as the outcome of evolutionary trial and error. Sequences that succeed are preserved and refined. Alternatively, it can be seen as an intricately tuned system, hinting not necessarily at a conscious designer, but at a deeper organizational structure underlying life itself. Scientists are even experimenting with entirely new genetic codes, alternative base pairs, synthetic amino acids, and modified translation rules. These studies demonstrate that other systems could theoretically function, yet they emphasize the remarkable efficiency of the natural code. It is resilient, versatile, and capable of supporting an enormous diversity of biological outcomes, all built on a single underlying script. Whether DNA was discovered or designed depends on definitions. It was not crafted by humans, nor is it discovered in the abstract way we understand mathematics or physics. Instead, it emerges naturally from the laws of chemistry and evolutionary dynamics. That it works so consistently, however, gives it qualities reminiscent of engineered systems. While this doesn't prove intentional design, it shifts the conversation. Rather than solely asking how life began, we notice that life operates as if based on a deep grammar, one we didn't create yet are still learning to read. Living organisms require protective barriers, not only physically but chemically. At the cellular level, this is the membrane. At the planetary scale, it is the atmosphere. Unlike a container wall, Earth's atmosphere is dynamic. It moves, changes, and regulates. While not alive, it functions as part of the living system. It retains essential elements while permitting controlled exchanges with the environment. Earth's atmosphere is mostly nitrogen, roughly 78%, followed by oxygen, argon, carbon dioxide, and trace gases. These proportions may seem ordinary, but slight deviations can disrupt the system. Excess oxygen can trigger uncontrollable fires. Too little causes suffocation. Without nitrogen, plant growth halts. Without carbon dioxide, photosynthesis ceases. These percentages are not symbolic. They are functional, maintaining the chemistry upon which life depends. This delicate balance did not appear instantly. It evolved over eons. The early atmosphere of Earth was vastly different, dominated by volcanic emissions such as methane, carbon dioxide, and sulfur compounds. By today's standards, it was toxic, yet it wasn't devoid of life. Microorganisms emerged and thrived in this environment, and over time, some began releasing oxygen through photosynthesis. That oxygen combined with iron in the oceans, forming rust that sank to the seafloor. For a long period, oxygen levels remained minimal. Then, gradually and eventually more quickly, they started to rise, a transformative shift known as the Great Oxidation Event, which fundamentally altered the atmosphere. The presence of oxygen enabled cells to generate energy more efficiently, making multicellular life feasible. However, it also drove extinctions, as organisms adapted to the old atmosphere struggled to survive in the new conditions. Life effectively rebooted, evolving under the new rules and developing new strategies. Oxygen didn't simply permit complexity, it demanded it. Even today, oxygen levels aren't controlled mechanically. They result from interactions and feedback between ecosystems, geological processes, and climate. Plants and algae produce it, animals consume it, fires reduce it, rock weathering sequesters carbon, and volcanoes release it. If one part shifts too far, the others adjust. The result isn't perfect equilibrium but a bounded, self-regulating variation. A system that pulses, cycles, and breathes in feedback loops. One of the most critical aspects of the atmosphere is its pressure. At sea level, it exerts roughly 14.7 pounds per square inch. This pressure keeps water in liquid form, enables effective gas exchange in lungs, and influences everything from boiling points to the mechanical stability of tissues. If pressure were much lower, water would vaporize too quickly. If higher, respiration would be hindered. Atmospheric pressure supports life, and in turn, life maintains the composition of gases that uphold that pressure. The composition of the atmosphere also governs how heat circulates across the planet. Certain gases, carbon dioxide, methane, water vapor, and others, absorb and emit infrared radiation. These greenhouse gases prevent Earth from freezing, yet too much of them causes overheating. The system is dynamic. Concentrations fluctuate, but largely remain within a range where life can persist. Additionally, the ozone layer, a thin atmospheric shield, absorbs the majority of the sun's harmful ultraviolet radiation. UV light damages DNA. Without this protective layer, mutation rates would spike, cells would perish, and life as we know it would struggle to survive. With just the right amount of ozone, dangerous ultraviolet rays are filtered out while useful light still passes through. The ozone layer emerges naturally from interactions between oxygen and sunlight, but it can also be weakened by human-made chemicals. That sensitivity isn't a defect. It shows how finely tuned the system is, relying on continuous chemical reactions powered by solar energy. The atmosphere is not static. It's in motion. Winds transport heat, moisture, and particles across continents. Jet streams guide storms, while ocean currents exchange energy with air currents. Together, they redistribute heat from the equator toward the poles, preventing the tropics from overheating and the poles from locking into deep freeze. This circulation shapes climates and keeps Earth habitable across diverse latitudes. Another essential process is the hydrologic cycle: evaporation, condensation, precipitation. Water vapor rises, forms clouds, and returns as rain or snow. That water replenishes rivers, nourishes soils, recharges aquifers, and sustains forests. The atmosphere drives this constant motion, binding together land, ocean, and sky, not metaphorically, but chemically and physically. It doesn't need central coordination. It functions through pressure, sunlight, temperature, and altitude. Yet the result often looks like orchestration. Air currents also carry microscopic passengers: dust, pollen, microbes. Some influence how clouds form, others deliver nutrients across seas, and some establish new ecosystems in distant places. These are not mere side effects. They are mechanisms of transport that enable adaptation, dispersal, and evolution. The atmosphere itself is astonishingly thin. Though it extends about 100 kilometers outward, Nearly all of its mass is packed into the first 10 to 15 kilometers. That slim band holds the air we breathe, the clouds we watch, and even the sounds we hear. Beyond it lies the gradual emptiness of space. Its thinness makes it fragile, but also functional. It admits sunlight, allows excess heat to escape, and retains just enough to sustain life. This delicate envelope also makes flight possible. Birds, insects, aircraft, all depend on air pressure and lift. Even seeds and spores use air as their vehicle. The atmosphere is more than a shield. It is an active medium where motion and exchange occur. And despite being so vital, it often goes unnoticed. Every breath we take is the outcome of planetary systems working together. The oxygen in your lungs might have originated from an Amazon rainforest tree or from a tiny ocean microbe. The air surrounding us isn't just emptiness. It's the product of billions of years of chemistry, adaptation, feedback, and motion. The atmosphere isn't conscious, yet its patterns show structure. Not random drift, but recurring cycles. Not stillness, but balance. A kind of regulation that suggests thresholds, memory, constraints. And even when the ingredients are correct and the chemistry aligns, timing still plays a decisive role. Not only in seconds or hours, but across immense scales, seasons, cycles, geological ages. On Earth, things don't simply occur, they occur in rhythm. Some fast, some slow, some measured in the gradual ticking of deep time. These processes aren't mechanical, yet they resemble a clock, not manufactured, but real. It is this timing that sustains function. Earth spins once every 24 hours, giving rise to day and night. That cycle sets the rhythm for sleep, activity, and photosynthesis. From insects to trees to humans, every living thing carries internal mechanisms synchronized with that rotation. Circadian rhythms, hormonal patterns, feeding and flowering schedules, all shaped by millions of years of repetition. The planet turns, and life turns with it. The year also has its own measure. A full orbit around the Sun takes about 365.25 days. Coupled with Earth's axial tilt, this creates the seasons. These are not superficial decorations. They govern migrations, trigger reproduction, regulate growth. Bears hibernate, birds migrate, crops ripen. Even microbes adjust their cycles to seasonal cues. None of this would be possible without steady orbital timing. Remarkably, Earth's orbit is unusually stable. Nearly circular, it ensures that solar input varies enough to create seasons, but not so much as to swing into extremes. By contrast, planets with highly elliptical orbits face intense summers and bitter winters. Earth's steady distance from the Sun keeps energy within a habitable range year-round, even with seasonal fluctuations. Yet Earth's motion is more complex than just daily spin and yearly orbit. There is precession, a slow wobble of the axis like a spinning top that takes roughly 26,000 years. There are shifts in obliquity, changes in the tilt itself, and gradual variations in orbital eccentricity. These cycles, collectively known as Milankovitch cycles, drive long-term climate rhythms. Ice ages, glacial retreats, rainfall shifts. Their timing isn't perfect but consistent enough to shape history. Even the Moon joins the system. Its orbit regulates tides, but also subtly influences the length of the day. Over billions of years, lunar gravity has been gradually slowing Earth's rotation. Days lengthen by a few milliseconds each century, a small change but one that accumulates across deep time. A billion years ago, a full day lasted closer to 18 hours. That difference mattered for life. It shaped how long photosynthesis could run, how internal rhythms aligned, and how heat was stored and released. Evolution didn't occur in a fixed frame of time. It adapted to a shifting one. Other rhythms played alongside. The sun follows an 11-year cycle of solar activity, marked by rising and falling numbers of sunspots and fluctuations in radiation. These variations ripple outward, influencing Earth's magnetic field, satellite systems, and possibly even subtle changes in climate. Geological processes unfold on much larger scales, tens or hundreds of millions of years. Tectonic plates drift, ocean basins open and close, mountains rise and erode, and mass extinctions seem to follow patterns, though their exact triggers remain debated. Life itself keeps time at the smallest scale. Inside each cell, molecular clocks run continuously, proteins rising and falling in repeating loops. These loops aren't just passive reactions, they anticipate. Cells don't merely respond to light, they prepare for it. Genes switch on and off at certain times, repair systems activate when stress is expected, and behaviors emerge not just reactively but on schedule. In humans, internal clocks govern sleep cycles, body temperature, hormone release, and digestion. Jet lag happens when the inner clock drifts out of sync with the outside world. Disrupted rhythms can harm health. The body needs order, not rigid but patterned, and that order ultimately comes from Earth's cycles. Even reproduction follows time. Menstrual cycles, gestation periods, mating seasons, all directly or indirectly tied to light and timing. Some of these links are obvious, others are buried deep in evolutionary history, remnants of ancient timing systems still quietly ticking. Beyond biology, there is cultural time. Humans built calendars to track the movements of the sun and moon. Farming depends on planting and harvest schedules. Religious traditions align with solstices, equinoxes, and lunar phases. Our entire sense of time, seconds, hours, years, is based on Earth's motions. Wristwatches are simply compact versions of cosmic rhythms. None of this implies intent. Earth doesn't know it spins. The sun doesn't know it shines. The moon doesn't know it drives tides. Yet the result is rhythm, repetition, reliability. Not designed, but sustained long enough for life to build upon it. What stands out is how these cycles interlock. Fast rhythms, day and night, sit atop slower ones. Seasons, years, orbital shifts. Beneath them lie even deeper cycles. Moving continents, rising mountain chains, aging stars. Each layer shapes the ones above it, creating a scaffolding not imposed from outside but arising from inertia, motion, interaction. That scaffolding creates windows of opportunity, times of warmth, light, stability when new life emerges. At other times it creates stress, ice, drought, competition, upheaval. Life responds to both but always needs time. Earth's consistency grants that time. Predictability is not the same as purpose. A clock doesn't need a watcher to keep time, but its regularity allows others to build upon it. Earth, in that sense, is buildable. Life, weather, chemistry, culture all rest upon steady timing. But none of it works if the rhythm strays too far. Some biological features show their history clearly, built step by step, tiny advantages stacked over generations. But others appear to leap ahead, not because they are unexplainable, but because they are so effective it's hard to picture them half-formed. The human eye is one of those, often cited as an emblem of complexity, where many interdependent parts must work together. Light first passes through the transparent cornea. The iris fine-tunes brightness, while the lens bends light to sharpen focus. On the retina, photons are converted into electrical impulses that travel along the optic nerve to the brain, where vision isn't simply received but constructed. Every moment, the eyes process millions of signals, sorting them into motion, shape, color, contrast, distance, safety, or familiarity. The eye is not just a passive light sensor but a dynamic optical system. The lens shifts to accommodate near or distant objects. Pupils expand or contract in response not only to light but also to emotions, and tiny muscles guide eye movements, keeping the world steady even as the body shifts. Vision, however, is more than optics. The brain overlays additional layers of processing, detecting edges, correcting colors, recognizing patterns. It fills in blind spots, stabilizes moving images, and interprets what we see in the context of memory and expectation. Sight is an interaction, not a snapshot. Evolutionary biology traces its origins back to light-sensitive patches on primitive organisms. Over time, those patches deepened, developed lenses, gained muscles, and refined focus. Even today, this progression can be seen in nature, from basic photoreceptors in jellyfish to the compound eyes of insects to the sophisticated vertebrate eye. Each stage provides an advantage even when incomplete. What's remarkable is how far vision has diversified. Birds of prey perceive ultraviolet light and spot movement over vast distances. Mantis shrimp see polarized light and colors unimaginable to us. Cats and owls thrive in near darkness. Squids evolved camera-like eyes distinct from ours, yet equally powerful. These are not primitive versions of sight. They are specialized, finely tuned systems. And vision is only one example. Bats and dolphins use echolocation, sending out high-frequency calls and analyzing the echoes to build three-dimensional maps in real time. Electric fish sense their surroundings through fields. Some insects perceive ultraviolet or infrared. Certain snakes detect body heat. These sensory systems don't just record, they interpret, filter, and adapt instantly. Even something as ordinary as the human hand demonstrates this complexity. Bones, muscles, tendons, and nerves combine for dexterity. The opposable thumb allows gripping and manipulating, while fingertips can detect tiny textures. Coordination between hand and eye allows for precision far beyond most machines. Playing an instrument, typing, or tying a knot. These are not brute motions but coordinated, responsive actions, constantly fine-tuned. Some parts of the body repair themselves. Skin heals, bones fuse, the liver regenerates. Others, like neurons, repair less easily, though even here flexibility remains. The brain rewires, forming new connections to compensate for damage. It adapts, not infinitely but sufficiently for survival. Development itself shows this resilience. Every human begins as a single cell, dividing, differentiating, and organizing into tissues, organs, and systems. The blueprint lies in DNA, but the unfolding is spatial, continuous, and interactive. Cells communicate, follow gradients, respond to signals, and build structure from within. The body isn't simply assembled like a machine. It develops from the inside out, from simplicity to complexity, constantly monitoring, correcting, and fine-tuning itself. Many processes unfold on precise schedules, organs forming at the right time, systems linking together at the right moment, transitions occurring when conditions are ready. If that timing slips, development can falter. But most often, it doesn't. It progresses with a precision comparable to engineered systems. That precision doesn't mean perfection, but it makes complexity repeatable and reliable. This level of accuracy appears in systems we rarely notice. The immune system identifies and neutralizes threats by recognizing patterns and storing memory. The endocrine system manages energy, growth, stress responses, and reproduction. The cardiovascular system distributes oxygen and nutrients with remarkable efficiency, instantly adjusting circulation to meet demands from movement, temperature, or injury. At the foundation of all of these are cells. Each cell is its own compartment, complete with membranes, organelles, transport networks, and waste systems. Cells follow instructions, respond to signals, divide, repair, or die, repeating these cycles endlessly. No single feature stands out as proof of design. Yet when these systems layer together vision, motion, balance, communication, the outcome is more than survival. Its capability, perception, creativity, and the ability to engage with the world in fine-tuned, adaptive ways. From the outside, humans may appear vulnerable, soft, slow, dependent on tools, but biologically, the body is both flexible and exact. It can endure long runs, heal from wounds, acquire language, master tools, nurture offspring, link memory with foresight, and balance emotion with reason. These aren't extra features. They're central to what it means to be human. None of this contradicts natural processes. Evolution explains it through variation, selection, and adaptation. Yet even within that framework, some traits stand out as remarkably effective, not only functional but versatile. Eyes do more than see. They adjust to brightness, track movement, shift focus. Ears do more than hear. They sense pitch, rhythm, direction. Bodies don't merely move. They climb, swim, dance, and write. These aren't random accidents. They're systems built upon systems, refined through time and interaction across many scales. This doesn't require intentional design, but the results work with a completeness that commands attention. Which leads to a deeper question, not just how individual systems function, but how they integrate. What keeps them in sync? What allows them to adapt to an environment in constant motion? Some processes happen because they must, yet together they form patterns that keep life resilient. Gravity pulls objects downward, rivers carve valleys, metal corrodes. These follow fixed rules, steady, predictable, mechanical. But not everything in Earth's story unfolds that way. Some events are singular, contingent, and could have gone differently. An asteroid collides, a gene mutates, a volcano erupts. We call them accidents not because they're errors, but because their outcomes weren't inevitable. Yet what stands out is how often those chance events reshape history in ways that look, in hindsight, almost deliberate. Take the asteroid that struck about 66 million years ago near today's Yucatan Peninsula. The collision unleashed energy beyond 1 billion nuclear blasts. It vaporized rock, ignited planet-wide fires, shrouded the sky in darkness, and collapsed ecosystems, bringing the dinosaur era to an abrupt end. That was no gradual evolutionary shift. It was sudden, violent, and decisive. But by erasing one dominant group, it opened ecological space for mammals to spread, diversify, and eventually rise. Without that impact, humans might never have appeared. That was one event, but far from the only one. About 2.5 billion years ago, the atmosphere began filling with oxygen. The cause wasn't destruction, but innovation. Single-celled organisms had discovered photosynthesis, using sunlight to split water. The waste product, oxygen, accumulated in oceans and air. At first it poisoned existing life, but eventually it powered new metabolisms, higher energy yields, complex cells, and ultimately multicellular organisms. One biochemical breakthrough altered the entire trajectory of life, not by plan but by consequence. Around 600 million years ago, multicellular life accelerated dramatically. Nervous systems, eyes, skeletons appeared. The Cambrian fossil record reveals a burst of diversity. Triggers likely included oxygen reaching a critical threshold and genetic innovations like regulatory toolkit genes shaping body plans. Whatever the cause, timing was crucial. A small shift forward or backward, and the environment might not have supported such complexity. Even tectonic drift plays a decisive role. The slow motion of continents redirects currents, isolates or merges species, opens migration paths, erects mountain chains that alter rainfall. These gradual movements reshape ecosystems and set the stage for natural selection, deciding who adapts, who merges, who vanishes. And then there's the moon, likely born from a colossal impact with a Mars-sized body. The event was chaotic and rare. Yet its outcome, a stable satellite, proved essential. The moon stabilizes Earth's axial tilt, drives tides, and moderates climate swings. Without it, seasons and weather patterns might shift too wildly for stable ecosystems to endure. None of these outcomes were guaranteed. They could have turned out differently, but together they defined the conditions under which life, eventually human life, emerged. These events weren't part of any schedule, yet their consequences stretched far beyond the initial moment. They weren't just chains of cause and effect. They were pivots, crossroads, moments where a single outcome reshaped what was possible afterward. Biology itself is full of what seem like improbable strokes of fortune. The emergence of DNA as a durable system for storing information. The rise of proteins capable of countless flexible roles. The arrival of eukaryotic cells, organisms with internal compartments like nuclei and mitochondria. That breakthrough likely began when one cell engulfed another, not to consume it, but to cooperate. A merger that, by chance, became permanent. That partnership unlocked the potential for larger, more complex life. Then came sexual reproduction, mixing genes to generate variation, speeding up evolution, though it required coordination between individuals. Later, the emergence of consciousness. Not merely behavior, but awareness, memory, foresight, and reflection. None of these were inevitable nor universal, but each was real, and each depended on a long chain of prior steps that could have gone differently. Even the human brain, with its layered functions, motor control, pattern recognition, language, rests on a biological history that began with simple responses to touch and light. Neurons had to arise first, then circuits, then interactions between regions. And every stage required the right conditions: energy, protection, and above all, time. Viewed this way, life resembles a filter. Countless planets may exist, many with water, warmth, or the right chemistry. But to reach complexity, then awareness, then civilization, a long sequence of unlikely events must align. Not just in any order, but in the right order at the right times. If it happens too soon, the system collapses. Too late, and the opportunity vanishes. That doesn't mean design, but it does suggest rarity. What unsettles is how narrow those margins are. If Earth were a little closer to the sun, oceans might have boiled. Slightly farther, and they might have frozen. If gravity were weaker, the atmosphere could have leaked away. Stronger, and the planet might have crushed itself into sterility. If water's chemistry differed slightly, cells might not cohere. If DNA folded differently, replication would fall apart. If a meteor had struck seconds earlier or later, extinction patterns would have shifted. When systems work, their dependencies vanish into the background. But when you isolate the pieces, it becomes clear how much had to align just to reach this version of life. Not flawless, but steady. Not ideal, but sustainable. The phrase fine-tuning often appears here, but that suggests purpose. What's visible is precision. A convergence of physics, chemistry, timing, and chance, stacked in a way that leaves little room for error. And yet, Against all odds, the system endures. It adapts, changes, it breaks apart and rebuilds, yet it does not collapse entirely. Earth's story is marked by accidents, extinctions, impacts, reversals, and dramatic shifts. And still, those very disruptions often give rise to new structures, greater diversity, novel pathways, and higher levels of complexity. The remarkable thing isn't that accidents are rare, but that so often they resolve in ways that let life persist. Sometimes barely, sometimes with surprising abundance. Long before telescopes, genetic sequencing, or computer models, humans wondered where the world came from. They traced the movement of stars across the sky, observed storms and seasons, witnessed birth and death. What they saw most clearly was repetition, patterns, cycles, and a sense of order that carried through time. And with regularity comes a natural question. Who or what set it in motion? The earliest answers were personal. Gods, spirits, ancestors, forces with names, intentions, and stories. In those worldviews, nature wasn't just a backdrop. It was a creation. Mountains, rivers, the sun, the moon, animals, and people were shaped by unseen agents acting with purpose. Sometimes that purpose was generous, other times unpredictable or destructive. But either way, it made events meaningful. A drought was not simply weather, it was a message. A fortunate harvest wasn't mere luck, it was favor. These ideas weren't random inventions. They were attempts to interpret something vast, something governed by rules but also seemingly responsive to human action. And while modern science has replaced those mythic explanations with testable models built on observation, the underlying impulse to seek agency behind structure hasn't disappeared. It has simply taken new forms. In ancient traditions, design was linked to divinity. A complex form suggested a maker. A harmonious order implied intention. You see this in Greek philosophy, where some imagined a prime mover, a shaping mind. You find it in Eastern thought, where the cosmos is less a product and more an unfolding, deeply ordered system. And you see it in sacred narratives, where creation is described as deliberate, even personal. Later, with the rise of monotheism and formal theology, the idea of design evolved into new language. Creation from nothing, divine purpose, sacred will. The universe wasn't simply formed, it was chosen. It had a beginning, a structure, and a goal. That perspective guided thought for centuries, not only in religious life but within early science itself. Many natural philosophers believed their work was uncovering the mind of God through studying nature. Then, in the 19th century, Darwin introduced another model, one that required no foresight at all. Evolution by natural selection explained how intricate life could emerge from simple beginnings, through variation, filtering, and time. It wasn't a revolution because it disproved design, but because it showed design wasn't required. Biological order could be accounted for without invoking intention. That didn't solve every mystery, but it shifted the framework. Since then, science has moved steadily in that direction. The prevailing view today is that systems, whether living, planetary, or cosmic, arise from the interplay of rules, matter, and time. Complexity from simplicity, not by construction, but through self-organization. At every step, the process is local. There's no overseer, just feedback, selection, and iteration. Yet even within that model, the sense of design lingers, not in the old sense of a watchmaker in the sky, but in the character of the results. The brain functions like a computer, the genome like a script, the laws of physics like an operating framework. These comparisons aren't exact, but they're persistent. We continue to encounter natural systems that resemble the engineered ones we invent. And that resemblance has become tighter. We no longer just borrow engineering language to describe biology, we actually engineer biology. We edit genetic code. We simulate ecosystems. We evolve artificial organisms inside algorithms. We design models that generate other models. In doing this, the line between natural and artificial design blurs. Artificial intelligence, once only imagined, now writes, paints, translates, predicts. It doesn't think as humans do, but it processes structure. It detects patterns and occasionally delivers solutions that astonish its creators. Algorithms adapt. Neural networks reorganize. Complex behaviors arise from simple instructions. Sound familiar? This doesn't make algorithms divine, but it raises a fresh question. Does design always require consciousness? Does order need a mind or only the right conditions? If machines can produce meaningful outputs without understanding them, then maybe understanding isn't essential for creation. And if nature can generate order without intention, maybe intention is not the sole path to complexity. That is where the conversation has arrived, not framed as science versus religion, but as competing models of emergence. Some propose the universe organizes itself. Others argue it was shaped, yet both acknowledge the outcomes are structured. Structure can be studied, described, replicated, sometimes even forecast. And it runs deep from physics to chemistry, from cells to consciousness. What's shifted is language. We no longer speak of a world built by hands. We speak of systems, thresholds, probabilities. But the underlying intuition remains. Function suggests form, and form suggests cause. That curiosity drives everything from simulation theory to the search for extraterrestrial intelligence. Whenever something works remarkably well, we look for a reason. The difference now is scale. Ancient accounts were local gods of rain, gods of fertility, gods of war. Today the questions reach the cosmos. Was the universe itself tuned to permit life? Could there be other versions where life fails to arise? Are we just the product of chance sorting? Or are we in a scenario biased toward observers because only observers can ask the question? That concept, the anthropic principle, doesn't solve the puzzle. It reframes it. If you exist in a universe with life, it's no surprise you can observe it. But that doesn't explain why such a universe exists at all. And so the cycle persists. From deities to algorithms to simulation hypotheses, every answer circles back to the same enduring question. The results look like systems that function. Not flawlessly, not always smoothly, but with a precision, coordination, and timing that can't be easily dismissed. At first, these were metaphors, the brain as a machine, DNA as a code, the cell as a factory. These weren't meant to be literal, only useful illustrations that made the invisible a little clearer. Yet, over time, the metaphors began to shift. They stopped being just comparisons and started to feel like reflections. As digital systems advanced, they didn't merely resemble biology, they began to act like it. Early simulations were modest. A handful of rules, a few moving parts. A digital ant tracing a scent. A flock of virtual birds falling into formation. Even then, something remarkable appeared. Complex behaviors emerged from simple instructions. Not because the behavior was pre-written, but because the environment permitted it. Interaction generated emergence. That same principle now drives everything from video games to climate modeling. We input data, we set boundaries, we let it run, and the system answers back. Sometimes it breaks, sometimes it surprises, but more often than not, it behaves in ways that echo the real world. Populations shift, settlements form, dialects evolve. Artificial agents discover strategies their designers never coded. Not through comprehension, but because the mathematics supports it. If artificial systems, starting from almost nothing, tend toward the same forms as biological ones, what does that imply? Are these patterns simply efficient? Or do they reveal something deeper, a universal geometry, an architecture that any system gravitates toward when conditions align? This is where the idea stretches further. Some suggest our own universe might itself be a simulation, not metaphorically but literally, a digital environment running on a hidden substrate. What was once science fiction has become a serious philosophical hypothesis, debated by physicists and computer scientists. If a civilization can simulate consciousness, the reasoning goes, then simulated worlds could vastly outnumber original ones. And statistically, it's possible we already inhabit one. There's no proof, but there are peculiar hints. Limits in physics that look like resolution. Matter and energy behaving as if quantized, pixelated. Measurements that collapse outcomes only when observed. Boundaries that resemble computation more than continuum. Perhaps these are simply properties of reality. Or perhaps they are signatures, artifacts of something deeper. There are hints that the system we inhabit has limits, patterns, and rules. Even if the simulation hypothesis is incorrect, it offers a useful lens. It encourages a new way of looking at reality. If the world behaves like a system, we can approach it like one. We can map its parameters, examine its rules, search for consistency. We are not assuming intent. We are recognizing structure. Virtual environments add another dimension. We now build digital worlds so convincing that the brain often treats them as real. Games, training modules, design platforms, all simulate scenarios that don't exist yet still produce meaningful experiences. In these realms, perception becomes the main variable. If the brain accepts it, the boundary between real and simulated begins to blur. Within those systems, we place agents, artificial intelligences that learn, respond, and adapt. They don't think as humans do, yet they process information, explore options, and even display pattern-seeking behavior akin to learning. It's easy to imagine a near future where simulations aren't just predictive but exploratory. Worlds where we create new chemicals, test medicines, develop novel designs, all inside digital frameworks, guided by systems that weren't programmed line by line but trained, refined, and shaped through selection. Here, the line between writing a program and raising a program, between architecture and emergence, begins to dissolve. This perspective doesn't replace the old questions. It reframes them. If reality can be partially simulated, then the difference between design and discovery narrows. Perhaps design is simply what emerges when conditions favor certain outcomes, and discovery is recognizing the structures that already exist. Simulations needn't be perfect. If they produce functioning, responsive, adaptive systems, they offer a form of parallel creation. One that can be studied by watching it unfold rather than asking who made it. When something appears structured, it's natural to ask whether it was designed. But the next question is more challenging. If it was designed, why like this? Earth isn't flawless. It works, but unevenly, fragile, full of trade-offs, blind spots, and peculiar choices. Organisms age. Ecosystems collapse. Natural disasters strike without warning. The same systems that support growth also permit suffering. If this is design, it is messy. That suggests design may not be what we traditionally imagine. We often assume a designed world implies intention, perfection, and rare exceptions. But nature does not follow that logic. The most successful systems aren't always elegant, they endure. They are good enough, stable, viable. Some aspects of Earth seem tuned for life. The atmosphere, axial tilt, abundant water. Others are indifferent. Earthquakes, viruses, genetic disorders, predators that evolve faster than prey that endure without adaptation, extinctions that erase entire branches of life. These aren't blueprint flaws. They are features of an ongoing, open-ended process. Even the human body, praised for precision, shows compromises. The spine, inherited from quadrupeds, struggles with upright posture. The eye has a blind spot where the optic nerve exits the retina. The shared airway of the trachea and esophagus creates choking hazards. The brain, brilliant though it is, remains susceptible to distortion, addiction, delusion, degeneration. Evolution explains this. Structures adapt slowly, often through modification and reuse. A solution that works is copied and adjusted rather than redesigned from scratch. This generates inefficiency, overlapping functions, unnecessary complexity, and vestigial organs, but also flexibility. A system that is good enough doesn't need perfection. So if we speak of design, perhaps it isn't the kind we are accustomed to, not pre-planned, not driven by a single goal. Perhaps it's more like an emergent architecture, shaped by constraints, feedback, and chance. In that sense, the question, why like this, transforms into, why has this version persisted? A very different inquiry. Scale matters too. Some patterns appear chaotic up close, but when viewed from a distance, the rough edges blend into coherence. Climate systems fluctuate wildly, yet over long stretches they stabilize. Ecosystems collapse only to reorganize around new species. Genetic variability introduces vulnerabilities but also builds resilience. Life overall has persisted for billions of years. That isn't perfection. It's durability, with plenty of room for awe and for unease. Even among finely tuned systems, many aspects seem arbitrary. Why does reproduction hinge on randomness? Why do beneficial mutations propagate so slowly? Why are cycles of starvation and competition so pervasive in nature? From a design perspective, suffering may not be a flaw. It might be integral. Pressure fosters adaptation. Scarcity promotes cooperation. Failure sparks innovation. Yet that interpretation implies a kind of moral distance, a system that progresses by letting components fail. Humans often envision better worlds, a realm without pain, aging, or extinction, bodies that heal completely, planets free of tsunamis or drought. If we ask why Earth wasn't made that way, one answer could be that trade-offs are inevitable, that complexity requires risk, and that self-modifying systems cannot be tightly controlled without losing adaptability. But that's speculation, assuming goals. The patterns we observe do not clearly indicate direction. They suggest survival. In human technology, systems are designed toward specific objectives: speed, efficiency, safety. Nature does not optimize like that. It adapts to what works under pressure. Some outcomes are elegant, others clumsy. Some structures ancient, others improvised. The brain is powerful but vulnerable. The immune system adapts but reacts. Intelligence allows planning yet permits anxiety. There is no single theme, no unifying principle, just a historical layering of forms building on predecessors without ever restarting entirely. If there is design, it is decentralized, distributed, layered, perhaps unconscious. The notion that Earth is designed does not require perfection. But what we see, systems that are beautiful yet occasionally brutal in failure, suggests that if design exists, it follows rules unlike human logic or goals, and perhaps even diverges from human values. It's also possible we are asking the wrong question. Design and randomness may not be opposites. Structure can arise without imposition. Feedback, replication, and memory may suffice to produce apparent intention. In that view, why like this shifts from meaning to consequence, not who decided but what enabled sustainability. Every system, no matter how detailed, tested, or modeled, reaches a limit where explanation halts. Not because there is nothing left to know, but because our tools have reached their capacity. And when we reach that limit, something else fills the space. Sometimes it is silence, sometimes curiosity, and sometimes faith. Science progresses by establishing boundaries, quantifiable, repeatable, observable. It deals with what can be tested. Gravity is not a theory because someone believed in it. It's a theory because it predicts what happens next. The same applies to thermodynamics, evolution, and electromagnetism. The power of science lies not in explaining meaning, but in its ability to predict. Yet humans don't live on prediction alone. They live on narrative, on purpose, on connection. When these are absent from equations, they often appear in other frameworks that speak in terms of why rather than how. For some, that is religion. For others, philosophy. For many, it is a blend of both, shaped by culture, family, language, and history. These systems offer ways to interpret not just how the world operates, but what it signifies. And advancing science does not erase them. They evolve alongside it. At its extremes, physics itself begins to resemble philosophy. Quantum mechanics does not merely describe particles. It describes probabilities, observation, and uncertainty. General relativity does more than explain motion. It reshapes space and time itself. These concepts challenge intuition, strain language, resist visualization, yet are real, confirmed by experiments and embedded in technologies guiding our understanding of the universe. Still, even these models have limits. No unified theory reconciles gravity and quantum mechanics. Dark matter remains a mystery. We do not understand why physical constants take the precise values that allow atoms to exist. These gaps are fundamental, not minor. Into them, humans project meaning. Some argue the universe simply exists, no deeper reason, no hidden message, a fortunate roll of the cosmic dice. Others perceive intention, not necessarily in the details, but in the very fact of existence, in the persistence of laws, the emergence of minds, the recurrence of order enabling reflection. Neither view can be proven, nor do they need to be. They are not scientific models. They are interpretive lenses. What is striking is how the same questions inhabit both science and faith. What is time? What is consciousness? What preceded the beginning? Where does order come from? These questions become spiritual when answers intertwine with values, identity, responsibility, or purpose. Belief in science also demands trust. Not blind faith, but confidence in method, rigor, and the assumption that reality is consistent, measurements matter, and cause and effect are more than illusion. It is not supernatural belief, yet it is foundational. Science does not validate itself externally. It functions because it presumes the world is knowable. Faith, in contrast, thrives when evidence is absent, providing story where data ceases. This does not make it less real. It makes it suited for different kinds of questions. Throughout much of history, science and faith were intertwined. Early scientists often pursued religiously motivated inquiries into creation, seeking the hand of God in natural laws. Only in recent centuries have the two been framed as opposites. In reality, most people do not inhabit one domain exclusively. Humans live in this intersection, trusting science to describe the how, while turning to other frameworks to explore the why. The most fascinating moments occur where the two overlap. When faith ventures into scientific claims, conflicts often arise. Yet when it speaks through metaphor, mystery, or meaning, it occupies spaces science alone cannot reach. Conversely, when science speculates about multiverses, simulations, or consciousness, it begins to resemble belief itself. This is not a failure, it is a boundary test, a sign that curiosity persists beyond the limits of a model. Many physicists acknowledge this openly. They describe the universe's laws as elegant, surprising, or beautiful. They highlight simplicity beneath chaos, symmetry breaking into complexity. Terms like fine-tuned describe how narrow the window is between a lifeless and a living cosmos, without implying a tuner. Others see randomness, a vast ocean of possibilities, with this one universe happening to function. The anthropic principle explains why we observe a life-supporting universe, though it does not explain why it exists at all. Still, the central question remains: is the precision we perceive a fact of nature, or a reflection of our interpretation? Are we reading meaning into structure, or uncovering meaning that already exists? That is where belief enters, not to provide certainty, but to propose, to imagine, to hold open the door. Not all questions require resolution. Some parts of life flourish when mystery remains. And so we arrive near the end, though not at a conclusion. The ultimate question is not whether Earth was designed or by whom, but how we inhabit it now with the systems we have inherited. The air, the water, the timing, the patterns, the opportunity to reflect, imagine, and create. The question never truly leaves us. It merely quiets for moments, in work, in urban noise, in habitual patterns. Yet something will always awaken it. A night sky, a fragile fossil, a perfectly timed event. Is all of this something we found, or something we were meant to discover, designed or emergent, built or revealed? These notions spring from different roots but often converge at the edge of what can be explained. If Earth is designed, it is perhaps the most intricate design ever encountered. Every molecule positioned, every cycle balanced, every feedback loop layered into the next. A system sustaining itself over billions of years, recycling and reshaping, enabling not only survival but understanding. A quiet structural miracle. If Earth is not designed, if it arose through the slow dance of physics, chemistry, and time, it is no less remarkable. It discovered itself, becoming a conscious planet, a process reflecting on itself. Life learned to ask questions. Either way, the result is the same. We exist, thinking, observing, creating tools, making sense, telling stories. We study cells, galaxies, and equations not because we are told to, but because we need to know our place. We are fully here, aware of the conditions that allowed awareness, able to reflect on the past and imagine the future. That rarity alone may be enough. Perhaps the power lies not in knowing, but in the ability to ask, because the systems endure with or without answers. The Earth's rotation, the moon's pull, the breadth of the atmosphere, the rise and fall of ecosystems, the continuous interplay of genes, memory, and environment. The rules remain, and now we see them. Observation requires not certainty, but attention, presence, a willingness to accept that some things are structured, strange, and awe-inspiring. Not because they exist for us, but because we can perceive them. That could be design. That could be chance. Either way, it is discovery, and it continues to unfold. Thank you for spending this time, not rushing, not concluding, but sitting with a question that does not need an answer to be meaningful. Whether Earth was designed or discovered, whether systems are intended or emergent, the world remains breathtaking. And you, here now, listening, breathing, aware, are part of it. Sleep well or think long, there is no pressure. The planet keeps turning. Patterns endure, and the questions remain for the morning. Good night.